There is an expression to remember the definition, that is lambda is equal to delta Q divided by delta L, or we can also write it as lambda is equal to Q divided by L. What is volume charge density? It is the charge per unit volume of a conductor, and it is given by rho is equal to delta Q divided by delta V. 1 by epsilon naught times the charge enclosed by the surface gives the electric flux through the closed surface, and that's the statement of Gauss law. Hello everyone, welcome to session 5 of chapter 1, Electric Charges and Fields. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. So we are studying about the properties of charges and the fields, laws which are applicable in the study of electric fields and many more. So in today's session, let us learn some more interesting concepts regarding electric fields and their properties. Now, we are going to study about the torque acting on a dipole expression. So, what do you mean by torque? We all know that it is a rotating force. What do you mean by dipole? We all know that equal and opposite charges separated by a distance of 2a, then we'll say it as a dipole. So, now we are going to derive an expression for torque acting on a dipole. So, when I say torque acting on a dipole, we must consider two charges which are separated by a distance of 2a. So, this is my dipole. I have plus q and minus q. They are separated by a distance here. From center of the dipole to this point it is A, from the center of dipole to this point it is A. So, A plus A is 2A. We all know the dipole moment can be represented by P vector and the direction is from negative to positive. So, here E is the electric field, and due to plus Q, the force acting at this point is F is equal to plus QE, and the force acting at this point is F is equal to minus QE due to negative charge. So, we have considered a dipole in uniform electric field, and we are going to derive a torque acting on dipole placed in uniform electric field. I hope the diagram is clear to everybody. So, I have considered an electric dipole of dipole moment P, which is placed in a uniform electric field E. As I told, the force acting at 2 points, that is force on plus Q is QE and force on minus QE is minus Q into E, because we know that F is equal to Q into E, because electric field E is equal to force experienced by unit positive charge. We have learnt about it in the previous class. So, since electric field is uniform, the net forces on the dipole is 0. So, due to the forces that are acting at different points, which results in the torque of a dipole. So, how do you find the torque? Torque is equal to magnitude of either force, that is F, and into the perpendicular distance between the two anti-parallel forces. You can see here, what is the perpendicular between two anti-parallel forces? So, this is a force and this is force. They are anti-parallel to each other, and the perpendicular distance between these two anti-parallel forces is BC. So, the expression for torque is equal to tau is equal to F into BC, where F is the magnitude of the force and BC is the perpendicular distance between two anti-parallel forces. Consider this triangle ABC. From this triangle we can write opposite by hypotenuse is equal to sin theta, that is sin theta is equal to BC divided by AC. So, from this we can write BC is equal to AC sin theta. So, I am writing tau is equal to F into, in the place of BC I am writing AC sin theta. So, we get BC is equal to AC sin theta. What is AC? We know it is a dipole distance, that is 2a. So, we can write BC is equal to 2a sin theta, and the above expression becomes tau is equal to F into 2a sin theta. So, tau is equal to F, in the place of F I can substitute QE, because electric field is equal to force experienced by unit positive charge, and from this we can write F is equal to E into Q or Q into E. So, we can write F is equal to QE, and hence tau is equal to QE into 2a sin theta. You can observe here I have a charge Q and I have a term called 2a. So, what is 2a? It's a distance of separation between dipole. So Q into 2A gives us a dipole moment, that is P. So P is equal to Q into 2A, and above expression becomes, in the place of Q and 2A, I am replacing P. So I'll get tau is equal to PE sin theta is the expression for torque acting on a dipole, and in vector form we can represent it as tau with arrow mark, which is equal to P into E. And this torque will tend to align the dipole with the field E, which means this torque helps the dipole to align with the electric field. So this torque depends on, from the above expression we can write, so the dipole moment, that is P, and also the angle between the electric field and dipole moment, that is given by theta. So the torque always depends on the dipole moment and also the angle between the electric field and dipole moment. So this is a very important term to remember. Tau is equal to PE sin theta, which helps you in competitive exams also. So let's move on to the next topic called continuous charge distribution. So what are the types of charge distribution? How does the charge distributes on any surface? So there are three types of charge distribution continuously, that is linear charge density, and it is denoted by the term called lambda. What do you mean by linear charge density? Linear means length. So it is the charge per unit length of the wire. So there is an expression to remember the definition, that is lambda is equal to delta Q divided by delta L, or we can also write it as lambda is equal to Q divided by L, that is the charge per unit length of the wire. When you consider a small unit length or a small length, that is delta L, then it is the amount of charge on the unit length of the wire, that is delta Q divided by delta L. Both the expressions are right. So here from this expression, delta Q is charge contained in a small line segment or small line element, that is delta L. So the SI unit of linear charge density, you can see here I have a term called Q and L. So what is the SI unit of charge? That is coulomb, and length is meter. So we can write it as coulomb per meter, that is the SI unit for linear charge density. And we have the next type, that is the surface charge density, and surface charge density is denoted by sigma. So what is surface charge density? It is nothing but the charge per unit area of the conductor, that is sigma is equal to delta Q divided by delta S. What is delta Q? Charge contained where? On a unit area element delta S. So charge per unit area element is surface charge density. What is the SI unit for the surface charge density? We have Q divided by surface area, that is A. So what's the SI unit of charge? Coulomb, and area is meter square. So when you take this to the numerator, you will get coulomb per meter square is the SI unit for surface charge density. And the next thing we have is a volume charge density. It is given by rho. It is denoted by rho. So what is volume charge density? It is the charge per unit volume of a conductor, and it is given by rho is equal to delta Q divided by delta V. We know the SI unit of charge is coulomb and the volume is meter cube, and we get the SI unit for volume charge density is coulomb per meter cube, and the expression to remember this is Q by V, or delta Q divided by delta V, which means the charge per unit volume of a conductor is volume charge density. Having an idea about the types of charge densities, now we have to derive the electric field due to a continuous charge distribution in terms of volume charge density. We are considering a volume charge density and finding the electric field due to a continuous charge distribution. But we know volume charge density is given by rho is equal to delta Q divided by delta V, that is charge per unit volume of a conductor. So from that we can write Q is equal to rho into delta V. The total charge is equal to rho into delta V. I'll take it as equation 1. So what is Q? That is charge. Delta V is volume element and rho is the volume charge density. So let us consider a point P which is at a distance of R from the volume element. I have taken a volume element here. So from this volume element, P is at a distance of R. So on which we are going to find the electric field. So electric field due to charge in this volume element is delta E is equal to 1 by 4 pi epsilon naught delta Q by R square into R cap, because we know the expression for electric field. Now we have considered this volume element on which the charge is delta Q, and hence the expression delta E is equal to 1 by 4 pi epsilon naught delta Q by R square into R cap. So what is R cap? It is a unit vector which will tell us the direction. Now delta E is equal to 1 by 4 pi epsilon naught. What is delta Q? According to volume charge density, that is rho is equal to delta Q divided by delta V, or we can write delta Q is equal to rho into delta V. So in the place of delta Q, I am substituting rho into delta V divided by R square into R cap, that is from equation 1. Now what is the resultant electric field at this point at P? That is the sum of electric fields due to number of small volume elements. That is from superposition principle of electric fields we have learnt, and we can just take all the volume elements, and when we sum up all these things, we will get the total resultant electric field. That is E is equal to 1 by 4 pi epsilon naught summation of all volume elements into rho into delta V divided by R square. So this is the expression for electric field due to continuous charge distribution considering volume charge density at a point P. So the next very important topic in electrostatics is Gauss law. So it's very important to know what is Gauss law and how it is different from Coulomb's law in electrostatic. So the statement of Gauss law says that the total electric flux, we all know what is electric flux. It is number of field lines passing normally through a surface. So the total electric flux through a closed surface is equal to 1 by epsilon naught times the total charge enclosed by it. That is given by phi is equal to Q divided by epsilon naught, where phi is the total electric flux, which is equal to 1 by epsilon naught times the total charge enclosed by it, or it can be written as Q divided by epsilon naught. So what is Q? It is net charge enclosed by the surface, and epsilon naught is the permittivity of free space. So this is the statement of Gauss law. To remember this definition, you must remember the expression. So when you know the expression, you can write the definition very easily. 1 by epsilon naught times the charge enclosed by the surface gives the electric flux through the closed surface, and that's the statement of Gauss law. So we all know that the electric flux phi is equal to E into delta S, that is total electric field passing normally through a surface area. Now I have considered a small surface area delta S where E is the electric field passing through that surface. So from that we can write delta phi, that is the flux, which is equal to, from this expression we know E is equal to Q divided by 4 pi epsilon naught R square into R cap. So I am substituting in the place of E Q divided by 4 pi epsilon naught R square into R cap into delta S. So this is the electric flux passing through that small area element delta X. Now how to find the total flux through the sphere, and that can be calculated by adding the small elements, all the small elements on the sphere, that is summation of all delta S into Q divided by 4 pi epsilon naught R square into delta S. So Q divided by 4 pi epsilon naught R square into summation of all delta S, that is adding all small area elements, will give us Q divided by 4 pi epsilon naught R square into S, where S is the total area of the sphere. Since we have considered the spherical surface, it is 4 pi R square. Now the total flux phi is equal to Q divided by 4 pi epsilon naught R square into 4 pi R square. I have substituted in the place of S, that is the total area of the sphere. So from this we can cancel 4 pi and 4 pi, R square and R square, and we remain with phi is equal to Q by epsilon naught, which is the statement of Gauss law, that is the total flux passing through a surface, a closed surface, is 1 by epsilon naught times the charge enclosed by the surface. It's very important to understand the term called Gaussian surface in the study of Gauss law. So what is the meaning of Gaussian surface? You can observe here I have different types of surfaces and imaginary surfaces. So it's an imaginary surface for which the Gauss law is applicable is called as Gaussian surface, or this Gauss law is applicable to any shape or any sized surfaces. That's one of the advantages over the Coulomb's law. Let us now understand how it is different from Coulomb's law, how the Gauss law is different from Coulomb's law. So it's very difficult to calculate the electric field due to a large shaped or large sized bodies with the help of Coulomb's law. So in such cases Gauss theorem is useful, and it is used in finding the electric field for the bulk substances or the bulk surfaces as well. applicable. So Gauss theorem is applicable for any closed surface of any shape, as I have mentioned. So these are the two important points to remember and the advantages of Gauss law over Coulomb's law. So one thing we have to understand here is flux due to charges situated outside the closed surface. Suppose if this is a closed surface, when the charge is placed outside the closed surface and the flux due to the charges which are situated outside the closed surface is not considered in the study of Gauss law. When the charge is equal to 0, when there is no charge, there is no flux, because the force experienced by charge is electric field. When the electric field is not there, field lines passing through the surface is flux, and when Q is 0, obviously the flux value will be equal to 0. So these are again two important points to remember in Gauss law. Let us now move on to another important topic, that is applications of Gauss law. Here we are applying Gauss law to the various surfaces. We are considering different conditions and we are applying Gauss law. And the first application of Gauss law is we are going to find the electric field due to an infinitely charged, uniform, straight conductor or a wire with the help of Gauss theorem. So you can observe here, it is an uniformly charged straight conductor or a wire on which we can observe the continuous charge distribution. Plus you can observe here. So we have considered an infinitely long, straight, uniformly charged wire where the charges are aligned linearly, and we have lambda is equal to linear charge density, which we have already studied in continuous charge distribution. So in this diagram, so plus are the charges on uniformly charged wire. So lambda is equal to linear charge density and E is the electric field. R is the radius of this surface. And what is P here? P is at a point which is at a distance R from the wire. So what is the direction of electric field? The direction of electric field is radial. And the Gaussian surface, what we have considered, an imaginary surface where we are applying Gauss law, is a Gaussian surface, and here we have considered a cylindrical Gaussian surface. So what is Q here? It is the charge enclosed by the cylinder, and the length of the cylinder is given by L. So this is basically, we are explaining the terms involved in the Gaussian surface. So now the surface area of the curved part. So you can see here, this is the surface area of the curved part, and that is given by 2 pi RL. So how to find the total electric flux? That is, on the Gaussian surface, the total electric flux is equal to the flux due to phase 1, flux due to phase 2 and flux due to a curved surface. Here the flux due to phase 1, flux due to phase 2 is equal to 0, but we have the flux due to a curved surface. So what is flux? It is phi is equal to E into delta S, that is surface area, or we can write E into A. So here E into area of the curved surface. What is E? It's an electric field. So area of curved surface is given by 2 pi RL. So our total flux phi is equal to E into 2 pi RL. So this is the expression for electric flux due to surfaces. Now from Gauss law, we know the expression, that is total electric flux passing through a closed surface is equal to 1 by epsilon naught times the charge enclosed by it, that is phi is equal to Q by epsilon naught. Now what is Q? We know the linear charge density is amount of charges per unit length, that is Q is equal to, we can write Q is equal to lambda into L from this expression. So in the place of Q, I am substituting lambda into L. So phi is equal to lambda L divided by epsilon naught. So this is my equation 2, where we know lambda is linear charge density. Now we have the expression for flux from 1 and 2. So we can compare these two equations because the LHS is same in both the equations, and we can equate the RHS of these two equations. So from first equation, I have E into 2 pi RL, which is equal to lambda L divided by epsilon naught. So from this we can cancel L and L. I remain with E into 2 pi R, which is equal to lambda divided by epsilon naught. But I just want an expression for E, which is equal to lambda divided by 2 pi R into epsilon naught. Or we can write lambda divided by 2 pi epsilon naught into R. But the same thing we can represent in vector form, that is E is equal to lambda divided by 2 pi epsilon naught r into n cap, that is n is a unit vector which gives us the direction, but in vector form we have to denote it by arrow mark. So here E is outwards if lambda is positive, as we all know the direction of electric field due to a positive charge and negative charge. So when lambda is positive, E is always outwards, and when lambda is negative, E is inwards. So in today's session, we have learnt about the various charges distribution, the torque acting on a dipole, and also the Gauss law statement, Gauss law expression, and the application of Gauss law. So in the next session, let us learn more applications of Gauss law by considering different Gaussian surfaces. Until then, keep learning all of you. See you all in the next session. Thank you.